Okay, if you are ready, I start again. Now, let's consider the case of a flame. The difference is going to be the mass flux across the flame. That is the main difference with the previous analysis I showed to you. Now, I put g equals 0, no acceleration. I just want to see what will be the effect of mass flux across the flame. That's all. It is just a complementary study of the previous one. Now, the equation is written here. You have a second-order differential equation for the Fourier amplitude of the wrinkles in terms of the wave number. And as a parameter appear in this equation the mass flux, which is simply related to the flame velocity. That's all. It's flame velocity times the density of the upstream of the gas, unperturbed. Now you have a second-order differential equation. Now, if you look to an equation in the form, as I call that a normal form, exponential sigma t, I am going to find such a solution. Sigma is the real part of sigma is going to be the growth rate or the damping rate of the linear perturbation. And the solution of this second-order equation is quadratic equation, is simple, you know that. And VB is the inverse of the density, so 1 over rho B, okay? And by definition, this term is positive. So you have a root plus here that tells you that there is a growth rate, a positive growth rate that does exist. And this positive growth rate took this form here. It is proportional to the laminar flame speed and to multiply by the wave number, that is multiplied by the inverse of the wavelength. So there's such a result, the form of this result could have been anticipated without any calculation, just by dimensional analysis. You ask the question, what are my dimensional parameters that I have in my in this problem? Essentially, are the density, no problem, but also a velocity, which is a laminar flame velocity. So you have laminar flame velocity, and you have a non-dimensional density jump. In fact, it is a density decrease because the density in the burn gas is smaller than the density in the fresh mixture. And so now, if you want to build the inverse of a time, which is the growth rate is the inverse of the time, the only way to do that is to multiply UL by the wave number. That to multiply UL by the inverse of the wavelength. There is no other possibility. So you should immediately conclude without any calculation. This is some bright people are doing that. They say it's not necessary to do the calculation because I know what it's going to be. And now the only problem is to be sure that there is a solution with a coefficient capital A positive. But as I told you before, you can anticipate that just simply by the analysis I gave to you. Let me remember. No, it is before, yes. Here. No. Okay. Remember that I show you a simple explanation of the fact that it is going to be unstable. So the real part of sigma should be positive. And now you know by dimensional analysis that the sigma should be proportional to ULK. There is no other possibility, which is UL divided by the wavelength 2 pi. Okay? So in a sense, you can have skipped this calculation just by thinking a little bit, you know. You could have skipped the calculation. Now, it's not quite true because you have to show that the sigma is real. You could have an imaginary part. There is no imaginary part in that you cannot anticipate. So this is maybe one of the reasons to develop the detailed analysis. Not only, it's also to find out. So this calculation is not difficult. Technically, it is simple. It is boring a little bit because there are many, but it is not very difficult. It's a simple calculation. So let's be back to Dario analysis. Now, what is the conclusion of that? That shorter is the wavelength, stronger is the instability. This is something crazy. Smaller is the wrinkle, stronger the instability. And this very interesting story. Landau, this famous physicist, did that calculation after Zeldovich produced the laminar flame speed. You know, that just I have explained to you yesterday. And you know, between Landau and Zeldovich, there was some, let's say, competitive relation. You know, both of them were top scientists, and you know, jealousy, something like that. And Landau was so proud to obtain a new fundamental result on flame that Zeldovich did not pick up. So he went to see him, and he told him, you see, look, your flame does not exist, because as the smallest wrinkles are going to explode. So the flame structure cannot exist. It should be turbulent. This was the conclusion of Landau in his paper. And Zeldovich said, okay, Professor, come to my lab, and you will see a flame. So now one has to explain why this Landau instability is not so drastic that we believe Landau. Because the analysis, the idea of Landau was, you know, if you have an instability with stronger instability, shorter is the wavelength, this means that you are going to explode the flame structure. And so he concludes a laminar flame doesn't exist. So this would make Zeldovich thinking, go to my lab, you will see that the flame exists. So, but now we have to understand why it is not so drastic. And this is crazy, because when you look to the paper of Landau, he knows the reason, he knows why it is like that. But what did he do? He was looking in the same paper to a flame on a liquid surface, liquid propellant. You know, the flame on a liquid propellant that vaporizes and burns. And then he takes into account, in the same analysis, the surface tension of the interface. And then he found out that there is a stabilizing effect in the short wavelength. So he knows the answer, but he was unable to find out that the same phenomena occur for a gas. He knows the inside, but he was so proud to show to Zeldovich something new, considering flame, that he did not insist on that part. But it was very strange when you read the paper of Landau to find that he has the right analysis. Just he has to replace the surface tension of a liquid by what I am going to explain to you, which is the diffusive effects inside the flame structure that is going to stabilize the small wavelengths. This is why laminar flame does exist and are not turbulent as concluded Landau. This is very strange because, and it is very strange that because I was so, you know, on one side, so Landau concluded, it was in 44, that the flame is necessarily turbulent, cannot be exist in laminar. And at the same time, he wrote that there is no real theory of turbulence. If you read the book of fluid mechanics of Landau, this is clearly said in the chapter of turbulence. He says there is no real theory of turbulence. It doesn't exist. You have approximations, many things that are not real theory of it. So, but it was, so this is, the flames, you know, are wonderful. Flames and detonation and so on. Let's say combustion is a wonderful part of the physics because, and as Professor Lowe told you the first day on the place, that, you know, flame also is an excellent, flame and detonation, let's say, combustion theory is an excellent start to any problem that you encounter in physics, any, you know, because you have everything in combustion. You have fluid mechanics, you have gas expansion effect, hydrodynamic, and you have diffusive effect. I will explain. These diffusive aspects are also very, very surprising. You will see. You will see. So now, what I say here, I say, okay, the analysis is interesting, but you know, you cannot go to very small wavelengths because you have assumed that the flame thickness is 0. So as soon as now the lengths, the wrinkles are going to be of the order of the flame thickness, you can no more consider the flame as an interface. All right. Now I'll give you just a simple consideration to make you understanding why, how taking into account the flame structure, you are going to stabilize, because it could be also the opposite. I will show you later on. But for the moment, assume that there is in the transverse direction. I will explain you that precisely in the next lecture. That you have a flux in the transverse direction, and this is going to give you something like diffusion equation, an additional mechanism producing a diffusion equation of the flame. And this, if you put, and now you see, such diffusion equation is going to give you a relaxating term in terms of the thermal diffusivity times the square of the wave number, okay? So now, if you put that in the analysis, this, the dash point, the dash line is a Landau, Dario Landau, it's linear, as I explained to you. And now, if you have this, let's say, curvature term, to a k-square term that is going to damp completely the instability for the very small wavelengths, that is larger k. Okay? So the hydrodynamic instability is dominant for the very large length, let's say length scale larger, length wrinkles larger than the flame thickness, but it is damped out by diffusive effect. But this is a very rouse consideration, and you will see that the things are not so simple. But okay. I will not spend so many time to that. Is the curvature effect, and to give you a simplified approach of that. The things, you remember when you neglect the modification of the frame structure, the modification of the mass rate crossing the frame, which is simply the flame propagation in a sense, this modification is no longer zero. And you can assume that this is, like I have explained to you, something given by a diffusion equation. If you put that, I will go fast because it is, I don't want to be, I have no time to give you all the detail. But you see now, this jump that you have here is balanced, in fact, by a quadratic term, a cubic term. Now, in this equation, remember, when I neglect the curvature effect, that is, I neglect this quadratic term in the last term here. Now, if you put this in it, and this is what is going to produce the exact calculation, because this is a half calculation that I gave to you. It's very spectacular. If you have this equation, you find that there is now kappa is the reduced wave number, reduced by the flame thickness, and now you have a term here coming from the acceleration g, depending the sign depending on if the heavy fluid is above or below the flame, depending on the propagation. And this is the inverse of the Froude number, and this G is simply, this scalar here is simply proportional to UL squared divided by DL, okay? That's all. But okay, now, if you look to the stability, and S is a reduced growth rate, which is reduced by the transit time across the flame, okay? The transit time of a fluid particle, tau L, across the flame, which is simply DL it is UL divided by DL. Now, this S now is, once again, a solution of a quadratic equation, algebraic problem, but now you have you can ask, you can say, okay, let me be back. Okay, you can say, oh, I want to see what is this this marginal wave number. Can I have an idea of how much is it? So to do that, it's very simple. You say, in that case, the growth rate should be 0. S should be 0. Now, I have an equation, just a quadratic equation for the wave number. I am going to find two wave number, where the growth rate is 0. All right? That's very simple. Here, now, this depends on G. If this G is sufficiently large, that is, if the laminar flame speed propagating downwards is sufficiently slow, there is no solution for this equation, and you are in that situation where there is no growth rate at all. Everything, the flame is intrinsically stable. It kills the Dario-Lando instability. Gravity plus curvature kill completely the hydrodynamical instability of flame. But this requires to have a very small flame velocity propagating downward. And then, if you increase the flame velocity, you go to a marginal case here, and then above this marginal case, you have two wave number. So you have a set, continuous set of wave number unstable, and if you go above, you find this situation here. It is written here. Now, all these things, in fact, this was known already by a scientist, an American scientist called Mark Stein. I met him, he was old also. He was old. He was of the age I have now when I met him. But he was still very clever. He understood completely this point. And it turns out that this has been proved experimentally in the 1990s. You see, in my institution, by Jeff Searby, who is the co-author of my book, and one of my PhD students, Joel Kinard. And you saw, and this was, let me tell you, when I met Zeldovich once in my life, I tell him, you know, Professor, because I was very impressed to meet himself, we found out stable planar flame. And you know what he did? He opened his and he took out our paper and he shows this picture. He said, I know. And this is just to tell you that when you are young, and when such a good scientist was interested sufficiently to what you did, to know exactly what you did, you are very happy. And this was done, you saw, a long time ago, you know. I was very young. And this is a flame propagating downward about 10 centimeters per second. It is very difficult to do that. Why? Because, as I'm going to explain you, such flame are very sensitive to quenching mechanism by its loss. So it's not an easy thing to do. And just you increase a little bit the flame velocity, this flame, you see appear cellular structure that are related to this domain, a small domain of unstable wavelength. So all this, what I have described here, was fully reproduced by experiments. Now, is the flame propagating upward? It's not difficult to show, but Zeldovich was working on that, in fact, that the flame is almost like a bubble. Not exactly like a bubble, but almost like a bubble. Okay? So now we are going to another flame instability mechanism, which is very, very interesting. And it is the thermodiffusive phenomena. And in this mechanism, when I start working in combustion around the 75, I start looking to this problem with my first PhD student, Guy Joulin. So I'll start to a general consideration concerning, without calculation, just simple consideration of what is called flame stretch. There are two mechanisms that modify the inner flame structure. You see, when here are the complementary profile of temperature and mass fraction of the limiting species in green. They are complementary. If you take such profile and you shift, what are you going to obtain? Transverse flux, because you see an opposite, transverse and opposite, because where the temperature is higher, the mass fraction will be lower. So you see, I have written here, you see, in red, in B, you have the temperature, the conduction, flux by conduction. In green, in that direction, you have the diffusion of species that is going to decrease the limiting species that is going to burn, because you diffuse it. So you have a competitive effects in the transverse direction between heat conduction, and this is heat conduction here. You see here is going to increase the temperature. But you know, if you increase the temperature, you increase the flame speed. So if you increase the flame speed, you restore the wrinkle. But, and what about the diffusion flux of mass? It's going just to do the opposite. So there is a competition to know, there is a competition to know what is going to happen. It's not clear. It's not as simple as I said before, that it's going to have a diffusion equation. Let's see, the coefficient of diffusion can change sign because of the competitive effect in the transverse direction. You see, here it's just the opposite. The heat flux is in the transverse direction like that, and the mass flux is in the transverse direction like that. So still competitive effect. All right. Now this was the first one. The first effect inside the flame was diffusion. But there is another effect, which is a convective effect that you have inside. Why you have a competitive effect? Why you have you need to, simply because you see the flow here. the flow here, you have a transverse component of the flow. You have a gradient here of the flow. So you have also an effect of the flux of the flow gradient transverse direction that you have to take into account. And to begin with, we are not going to take into account this effect and just look to this effect here. And this was done first by Zeldovich too. He did that. And I will tell you a story about that. So one is going, okay, let's now, this is the general basic idea I want to develop in my calculation. But to do that, I would like to introduce you some geometrical consideration considering flame stretch. The flame stretch, we are going to find out that the normal burning velocity minus the laminar burning velocity in the planar case is going to vary linearly by the proportional to the strain rate, the rate of stretch of the flame surface. It's not going. Okay, I reproduce here a calculation which is well presented in the bachelor book, fluid mechanics, for example. Okay, well, what is a flame stretch? What is a flame surface? You know, flame, consider a small flame surface. I put a square because it is two-dimensional, okay? This is why I put delta square. It is because it is two-dimensional. So an element of surface, the stretch rate of that is simply the time derivative of this element of surface divided by this element of surface. That's simple. Now, you know, now an element of volume is the element of surface times a small distance in the normal direction. Okay, this gives you a volume. And why I use a volume? It is because I know what is going to be the relative variation of volume. As I told you in my first lecture, it should be the divergence of a flow velocity. By definition of the divergence of a flow velocity is just the rate, the reduced rate, not the rate of change of the volume or of the density, because constant you just inverse. Now, if you take the time derivative of this quantity, of this volume element, you have this. Simply, you have the relative thing. It is the growth rate or damping. It is the stretch rate plus the stretch of the thickness in the normal direction of the surface. Okay, and now you use the fact that the continuity equation told you that this relative volume change is going to be the divergence of the flow. Now, this is this term here. Now you have to compute what is this thickness here, the rate of change of the thickness. And this is easily, you say the rate of change is simply the difference of flow velocity just minus, you know, delta, the small increase of thickness minus the unperturbed thing. So you do that, you develop, and when you do that, you obtain that the growth rate of the thickness is related to a tensor, which is grad UE, scalar NF, and this is a scalar, you know, a matrix you multiply by the same vector in front and behind. This is a scalar. So this, now you put that and you use the fact that the continuity, thanks to the continuity, you know what is going to be the rate of change of the volume, and you obtain from the stretch rate here this equation, two terms. One coming from the divergence of the flow, and one coming for what is called the stretch rate, this on the right-hand side, which is due to the gradient of the flow velocity in the normal direction. Now you look to a first-order correction in such a way that you are going to develop this equation here. You just develop that, and you obtain in that case, you know, you develop linearly this, what I did, and now you obtain this relation, which is similar to this one, where you have now you make appear the gradient of the normal. What is the gradient of the normal in geometry? What is the gradient of the normal of a surface? Nobody knows? It is simple. It has a simple simplification, signification. You know, this where is it? Okay, it's not the gradient. It is a divergence. Stupid. It is a divergence. What is the meaning of the divergence of a normal of a surface? What is it? Yes? Must be the tangent. No. It's, you see, you take the normal. Ah, you mean, this is a gradient, but I am looking to the divergence. So I say something wrong. The divergence of the normal is the curvature radius of the surface. This is a general, you can, it's easy to show, eh? You just do your calculation yourself, you will find that. And when you know that, and when you take into account that the fluid is incompressible, this divergence of U should be 0 on the flame, and you take into account that it's a differential geometry result, that the divergence is the inverse of the curvature, it is a curvature radius. You have two curvature radius in two directions. This is a masterpiece of Gauss, this famous German mathematician, Gauss. He was working on flame geometry, and he was showing this result in the 19th century. So now, so you have two terms. You have one term which is associated to the radius, and one term which is associated to the strain rate, which is related to the gradient in all the direction of the flow. N is a normal. Don't forget that N is a normal. Now, you have two interesting limits. One interesting limit is when you have a flow impinging a surface. Let's say a flame impinging on the surface. Now, to first approximation, the flame is planar. So this term is 0, radius infinity. So you are left with a strain rate. This is why such configuration is used in the laboratory with two counter, let's say, two counter with burn and not burn and so on. Burn gas and fresh mixture going, or a fresh mixture going against a planar. So this is used many times in the laboratory to measure this strain rate and to see what is the effect on the laminar flame speed. And this is a curvature effect, which is, for example, a pure effect when you have a flame growing, a flame surface growing, the radius is growing like that with burnt gas at rest. So you have this. In that case, this term is 0, and you are left with the radius. So these two terms can be measured in experiments. This is what is important. Now, I will not do the calculation because this becomes technical and it's not so interesting to, if I do that, I will spend my lecture to explain all this calculation. There are technical, but asymptotic methods are relatively complex. Now, it turns out that is something that few people understood, even now. When you discuss with people involved in flame dynamics, few of them know what I am going to say. It turns out, if you use a one-step Arrhenius law, you can show precisely that you have when you look for the modification of the laminar flame speed, you have to obtain only number called Markstein number relating this effect here. that in a sense, the effect of the curvature on the frame speed is the same for the one-dimensional, for the one-step model with an Arrhenius law. The curvature effect play exactly the role with the same coefficient as the strain rate. So you have only one number here telling you how the normal flame speed is different from the laminar flame speed without any gradient, and it is just proportional to a number, and this number is called the Markstein number. This Markstein number have been computed. I did that. I think I was the first one to do that with Foreman-Williams in the simple case of conductivity constant. So I forget that its conductivity can vary with the temperature, small, but it varies like square root. So, but now, then a little bit later, we took into account the variation of the conductivity. This lambda depends on theta. Theta is a reduced temperature. And here is the expression of the Markstein number. What is very nice that the Markstein number is going to depend of the departure from unity of the Lewis number. Okay, here you have this expression. Okay, this term here, excuse me. This term here, D, and this term here, or G, D or G, are constant. So are constant characterizing the fluid mixture. Now, what is important here is the dependence on this number here in the Lewis number. This L is the reduced Lewis number minus unity multiplied by beta. Why in the calculation this number appears? It is because you are working, as I showed you before, in the limit of large activation energy, but now with Lewis number close to unity. You have what we call a distinguished limit. You make beta, the activation energy, go into infinity, and you make the departure of Lewis minus 1 going to 0. In a sense, you assume that you are looking to a solution where the departure of unity of the Lewis number evolve with the activation energy like the inverse. This is what you are looking at. And here are the results. There's no. Now, something that few people look at, because I guess my paper was complicated. I have to confess that this paper here is complicated to read. It turns out, but this was known by experimentalists, by people in England. They know that right at the beginning that the Markstein number is not the same for the curvature effect and for the stretch rate. It turns out that there are two Markstein numbers. One different Markstein number, different for the curvature and different for the strain rate, flow strain rate. You have to, they are different and they are the same only, and this is something that is interesting because what I did here, I developed theory with only one-step reaction, you see, governed by Arrhenius. There are some limits to that. And the limit, for example, is that with this one step, you have the same Markstein number. As soon as you have two steps, for example, that's what I did now you have two Markstein numbers. And in fact, this was understood by, it was proved in fact, in numerics and experiments, I don't remember the name, in England, in about the same time. But now, when you discuss with people in combustion, they forgot that. And this is, and in fact, it turns out that you may have a large difference between these two numbers. And to my opinion, there are a lot of work to develop still on that problem. Now, not only the Mach number, the Markstein number, I say Mach number, Markstein number is not the same for the curvature and for the flow strain rate, but also, and this is another point that you have to be careful when you analyze the experimental result. Also, it depends where you are looking at. If you are looking in the fresh mixture or in the burn gas. This is because, you know, this is because this gradient is different on the both sides. So one has to be careful with this. And there are experiments very simple that eliminated one of the two and keep only one. For example, if you have a flame steady out of stabilized out of a small duct of fresh mixture, right? And the flame, you have a spherical flame outside, which is stabilized at the velocity of the gas, which is equal to the laminar flame speed. And now in that case, it's easy to prove that now the difference of flame velocity is the difference of these two Markstein numbers. Not difficult to prove that. But on the other side, if you are going to look to a flame expanding with a burned gas at rest, now it's easy to show that the Markstein number is this one, is the one concerning the curvature effect only. So this, you know, when you know this, you can develop a lot of interesting experiments to different flames. Now, no, I have 10 minutes more. Now, let me go to one of the very interesting problems. It is the thermodiffusive instability of flames. So, in order to understand this possible instability due to the transverse diffusion that I have just explained to you by hand, I kill out the fluid mechanics to begin. No fluid mechanics. If there is no fluid mechanics, I have again to solve only reaction diffusion equation. All right? One for the temperature, one for the species. But I will start with the one-step reaction model in such a way that I define the progress variable, which is the concentration, mass concentration of the limiting species divided by its initial value in the fresh mixture. And I use also the non-dimensional temperature, which is defined here, which varies on 0 to 1. And here, the psi is also vary. This psi, the reduced mass fraction, is also going to vary between 1 and 0, because in the initial mixture, y equal yu, 1, and when you have burned everything, Ey is equal 0, so psi equals 0. So now you have a similar equation as the one we studied for the planar flame propagation. Similar, quite similar. Now, because I killed the fluid mechanics, I assume in this equation that I will neglect the variation of the density. This is a strong, very strong assumption that is not realistic. But he will put in the light the effect I want to show to you. And then we will take into account the variation of rho in the second step. But I will not present that. It is very technical. But this one is easy to do. So now, what is going to be important is the difference between the molecular diffusivity D of the limiting species and the thermal diffusivity dt of the mixture. Okay? These equations are the same, almost the same, with the same, except that these coefficients are different. These thermal diffusion coefficients are different. That's the only difference. To begin with, you have to be back to the laminar flame speed planar to see what is going to be the effect of a difference of density. This is very easy. In the planar case, you are solving exactly the same problem as what I did with Lewis equal 1, but it's a little bit more elaborated. And you find that the relative modification of the laminar flame speed divided by the laminar flame speed for Lewis equal 1, when you use the beta Lewis minus 1 for the unity, is, no. For that case, it is not necessary. You find out that this is square root of Lewis. The difference is square root, this Lewis equal 1, this is the previous result that I derived with you. When you take into account that the Lewis number is not equal to 1, the Lewis number, I remember, maybe it is not written, it's the Lewis number is the thermal diffusivity, it is not written, is the thermal diffusivity divided by the molecular diffusivity. Okay? This is what is called the Lewis number. And this is different from 1 in that case. So here are the equations. Here you will define the Lewis number. And now the asymptotic theory you are going to develop, and this is a crucial point, is that you are considering difference of Lewis number minus unity small of order 1 over large activation energy in such a way that in the limit of beta going to infinity, this number here is a constant. This is what we call an asymptotic analysis. You link the parameter in the limits in a clever manner. You have to be clever to that. You have to anticipate the result. As soon as you have anticipated, then you do that and you develop the calculation. The clever point was there. In fact, this clever point, when you read the analysis of Zeldovich, is not so clear in the analysis of Zeldovich. He did not, he did not like to discuss of asymptotic and so on. But in that sense, the analysis is not perfectly clear. There is, but the result is right. So if you do that carefully in asymptotic methods, now here are the key point of the method. The Lewis number is for the 1 over beta. In that case, why you put that? It's because you don't want that the variation of the flame temperature be too strong. Because if it is too strong, because the dependence in the temperature, burn gas temperature of the flame speed is exponential. So if it is too strong, the variation that you are looking at for the difference of the laminar flame speed with Lewis number equal 1 and not, you will find something that is exponentially large or exponentially small. So you have to be clever to say, no, I want to have a difference of order unity. In that case, you have to put this asymptotic analysis to do carefully the thing. Now, if you, it turns out that this is also a point, you know, this paper here, 79 paper, I developed with my first PhD student. He was a very bright student. I was very lucky to have, when I start combustion, I start with him. And I was very, very lucky to have such a bright student because we start together, the combustion. I did not know anything in combustion. I was working in my PhD on statistical mechanics, and I did not know anything about combustion. And my student also did not know anything about it. But he was so bright that together we succeed to develop things carefully. What we do is to show that in the asymptotic analysis, you have two jumps. So the first jump was known already. You know, this jump here that you have, this jump is a slope here that will depend on the flame temperature. You know, this is related to the flame speed. Okay, but the other that you have to use, and this is something that it's not well developed in the literature. Few people know that, except the specialists in asymptotic analysis. And let me tell you that there is no more. I think I am one of the last of Mohicans, you know, Mohicans, knowing what is an asymptotic analysis in flame, something that, not exactly that, but almost. And with this student, we develop exactly with different cases, and we show that you have two jump conditions. One, it is clear, it was known by Zeldovich, and the other was trivial for Zeldovich. The other tells you what is the conservation of the total energy. Total energy, including the chemical energy. And because in the reaction rate, excuse me, in the reaction sheet here, you have only diffusion as a process, and reaction and diffusion. There is no convection. So now you see the sum of these two tell you that you have, that the conservation of energy, this gives you the slope here. And it turns out that in order to obtain a flame variation, temperature flame variation of order 1 over beta, this should be true at the first order in the expansion of 1 over beta. And this is something difficult to understand. I don't want to emphasize too much here. I just tell you that if one of you, I hope so, I don't know, want to develop asymptotic analysis, they have to be careful, and they have to go back, not to the paper with Julien, I think to the paper with this book, where this is well developed and well present in details for the students, for the PhD student. Now, as usual, oh my goodness, I have to stop. As usual, I finish here. What you have to do is to work with non-dimensional quantities. Non-dimensional is for the velocity, for the distance. It should be divided by the laminar flame thickness. The time should be divided by the transit time of a particle, fluid particle, across the flame, which is simply the flame thickness divided by the laminar flame speed. And then you have the equation, the reduced equation written here. There is no, the only parameter you have is now the Lewis number. So this is, for mathematicians, it's good to know that you have only one parameter in your system of equation. That's all. Okay, thank you very much. We have 15-minute breaks now.